All right, looks like our numbers are stabilizing, so let's go ahead and get started. Thank you everyone for joining us today. I'd like to welcome you to today's CNCF webinar, Operationalizing Kubernetes Security Best Practices. I'm Caitlin Barnard, Marketing Manager at CNCF, and I'm going to be helping to moderate today's webinar. I'd like to welcome today's presenter, Connor Gilbert, Senior Product Manager at StackRox. So just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. So if you have any questions or comments throughout the webinar, there's a Q&A box at the bottom of your screen. So please feel free to drop in any questions that you have, and we're going to save those to the end, and then we will get to as many as we have time for. The session is also being recorded and will be sent out afterwards along with the link to the slides. So with that, I'm going to hand it over to Connor to kick off the presentation.
Hi, good morning, everyone. My name is Connor Gilbert, and as Caitlin mentioned, I work on the product team at StackRox, a container and Kubernetes security company based in Mountain View, California. I'm excited to spend some time with you today talking about important topics in Kubernetes security. So before I was a product manager, I was an engineer, and I operated a few Kubernetes environments in previous jobs, even back on Google Kubernetes engine way back in maybe 2015 when it was in beta, I think. And I thought I had things figured out then. Now, after diving more deeply into container and Kubernetes security for a few years and seeing a lot of the on-the-ground realities of how containers are deployed across a variety of enterprises, I'm not so sure I understood everything as well as I thought back then. And in the meantime, Kubernetes and its related projects have been evolving at a pretty rapid clip. In that vein, I'm mindful today that we have folks joining us with a variety of roles and experiences, and that there's always more to learn in such a lively ecosystem like Kubernetes and Cloud Native. I want to speak to everyone here, and I will do my best to be clear and to avoid shorthand. If I slip up and do leave something confusing, please ask a question so that everyone else can benefit from the clarification. So with that, let's jump in. Today, we'll answer 5 questions before wrapping up with Q&A time. The first is, how does Kubernetes change security? It's obvious that when you start changing around all the parts of a stack, the way that you do security will change. We'll talk through that. Next, how does cooperation work in a Kubernetes stack? Or what about all the people? Next, what can I do to improve the security of my infrastructure and then my applications? And finally, what are some Kubernetes controls I could consider adopting in my environment? Zooming out a bit, if you're a person who cares about security and your organization uses Kubernetes, we hope you'll see some of the power and not just the new challenges that it brings. Even if it seems like everybody else is concentrating on getting things out the door and changing up the stack for the heck of it, we think there are ways to use containers to get to an even better place than you were before. And perhaps you can bring techniques like the ones we'll talk about back to your teammates and help lead a conversation to improve overall security. So let's jump in. How does Kubernetes change security? It's worth explaining a bit of what we're talking about first before diving in. I'll cover some of the ways containers can challenge existing security programs, but on the flip side, the opportunity they pose to enable finer-grained, more automated security enforcement. If you're already an expert, please bear with me for a moment while I explain a little bit of the backstory. At a very high level, you can think of containers as the next step in the evolution from physical hardware to virtual machines. Infrastructure operators want to pack workloads closer and closer to get higher utilization, and developers, and especially the people employing them, want to deliver more value faster. Containers, especially when used with an orchestration tool like Kubernetes, help them do that. In a sense, containers are just a repackaging of existing things. Linux processes, control groups, namespaces, layered file systems, cryptographic hashes, virtualized networking, and some other stuff. But containers really took off when it got easier to use all of those tools together. Developers could package up applications into images with all the dependencies that they need, then share and run those images as containers with configurations that were easy to commit into version control and to share with others. And the containers would, for the most part, run the same way, whether they were on a laptop, in dev, in production, because they had a defined clean slate initial file system and configuration. And once people began to see this, orchestrators like Kubernetes and other tools started to appear, helping to handle scheduling, fault tolerance, storage, and other issues that creep up once you get out of the lab. So how does this change the security game? Well, containers often bring greater scale with them across a number of dimensions. The way apps are built is changing, and many apps are getting bigger, much bigger, and more complex. Before, you might have had one monolithic process with relatively isolated network activity, though now to achieve bigger scale or higher availability, or to leverage a managed cloud service and things like that, you may have a lot more moving pieces. And that means there are more things to understand before you can really grok what's going on in your app. But the scale comes in the human realm too. There are more cooks in the kitchen now. Dev, sec, and ops might all be operating in the same cluster, trying, or not, to stay out of each other's way. And a successful security hardening and detection effort has to recognize that context. On top of that, the landscape has also shifted, we think, in a way that can leave security as an afterthought. If dev and ops own the cloud account and operate the Kubernetes cluster, for instance, security doesn't have some of the familiar hooks that they have into the old process. So much of the infrastructure is software defined and outside of the reach of whatever controls that might have been set up before. But it's certainly not all bad news. Containers in Kubernetes, especially the standard APIs, can actually help you do security better. They don't necessarily allow you to do anything that wasn't strictly possible before. You could do many of the same things in different stacks or in different ways, and some people did. But we do think they make certain practices more feasible. We would have had a lot harder time getting the same level of visibility and, more importantly, a harder time iterating on and testing those config changes without a stack that, say, enforces declarative configuration the way Kubernetes does and enables quick changes without costly rebuild cycles. As in a lot of other realms, security for containers is a bit of a configuration problem. There may be some places where we need new technology or new features, but there are also already so many ways to configure guardrails, limits, and security barriers, and often the problem is really how to operationalize enough of them to achieve the desired level of security assurance. If that sounds wrong, just a reminder that anytime somebody makes a security feature, somebody else jimmies the door open. This is a satellite news truck, which you can see in the museum in Washington, DC. It was pretty cutting edge tech in the mid-80s. Seems pretty neat. And if you look at the display case, you see some sort of machine. Looks like it does some broadcasting. It's got an antenna. It's got a passcode on it. Okay, cool. I'm with you. Wouldn't want anybody sending unauthorized satellite broadcasts, right? But if you peek behind it, somebody decided their JIRA ticket for secure passcode distribution wouldn't come in before the end of the sprint. I get it. I've been an engineer for most of my career, and that mindset is understandable. We've all had deadlines before. But at StackRox, we've also personally seen that many companies never get beyond those default configs, even if they're sophisticated in other ways. A lot of people are stuck with the defaults, but you don't have to stay there. So it is important that as a community, we continue to innovate and make more controls available, sure. But our experiences also tell us that many people could up their game with the knobs they already have available to them. So there's a fast path to value for most folks out there, even without changing infrastructure components. Another promising aspect of this is that security relevant configurations live right alongside the configs that say how the app operates. So while you're developing a new lockdown profile or a new control, you can test it in the development or testing cluster the same way you test a code change. You can even iterate on security configs on your laptop if you're in a local cluster. Projects like Minikube or Docker for Mac make it easy to do that. And of course, running Docker on Linux doesn't need a special program. If an app is changed to require some new privileges, you can review that same diff in the pull request with the code change, so the implications of that change are clear. Next, if you're also using microservices design patterns, each atomic unit of your app will be smaller and can be locked down further. Then, when the pieces of your app are talking on the network, instead of with function calls within the app, you have a greater ability to monitor and control them, regardless of the language or the app frameworks that you use within each piece. It can be a lot easier to spot anomalies when you only expect an entry point process and maybe a few others, which are not the case with your old sort of stack. And these apps tend to be built to tolerate both replication and the failures that one would expect in a large distributed system. So response can often go forward with less painstaking investigation because Kubernetes can help you recover. So really, as people from the ops and security communities, my StackRox colleagues and I are really excited to see the broader use of Kubernetes and the design patterns that come with it. We think that containers in Kubernetes can really help a lot of enterprises up their security game. And we believe there's a lot of untapped value in the configs that are already available. But of course, we're excited to see new developments throughout the tech stack as well. Let's move to our next question. How does cooperation work in a Kubernetes stack? It's sometimes easy to talk about security or DevOps or workflows or other ideas without remembering that no matter what software we put in place or what automatic triggers we configure, they're still people. And people who are experts in other areas might not yet know how to apply their existing knowledge to a new stack. That's usually not because they're Kubernetes doubters or because they're Luddites stuck in the past. It's often just because Kubernetes has come into the organization through a different team, and they haven't had the time or the resources to learn a new system. Imagine your first time writing a Kubernetes deployment. It might have seemed a little odd. Along those lines, one of the concerns our customers often tell us about is things move too fast for the security team to keep up. And that can be true. But we'd argue there's also an opportunity here. Faster changes are often individually smaller, giving you a better chance to keep up. And faster changes that roll out through a repeatable, rehearsed process also means that security fixes and patches can be rolled out faster too. Your security improvements don't have to wait to the next big downtime. We find that teams can get to a place where they feel confident in their overall security posture through a mix of organizational policies, standard operating procedures, and real-time monitoring. It's good too. There are other good reasons for teams across the stack to make the investment and become familiar with Kubernetes. Compared with other workflows that might have been a little bit more idiosyncratic at each company, folks who get over the Kubernetes learning curve end up with a more broadly applicable skill set, regardless of which team they find themselves in. And an organization's adoption of a more consistent stack can help security teams scale themselves across the org, even as the company scales out their operations. Even if you're operating at a small scale now, investments you make now in common understanding, communication, and empathy will pay a lot of dividends later. I don't think we talk about this stuff enough, and we especially don't invest enough in empathy. But it's really important to understand where each group of folks is coming from, what their incentives are, what they want to see out of the container infrastructure. Sometimes we don't even say what we're really thinking out loud, like not just things are moving too fast, but I'm afraid we'll miss something. And on the other side, for the security folks here, if you hear pushback like this from DevOps, I don't want this security feature deployed in my cluster, it's often not because people don't want to be secure, but rather they're afraid that it will stop them from recovering from an outage. They can't do their job because of a security feature that you're advocating for. So just like your application might have taken some time to migrate to containers or Kubernetes, so might people and org structures. That's a whole other talk by itself, but do keep it in mind when it seems like somebody just doesn't get it. They might just not understand how this stack can help them do their job, and they might be concerned about something you're not thinking of. Working together, especially if you leverage native Kubernetes controls and establish common procedures and expectations, can help get everybody on board and speaking the same language. I'll shift now to some practices and mindsets you can adopt to improve your security posture. I'll cover infrastructure first before moving on to application workloads. The line can be a little fuzzy, and there's some overlap, but I think a division can be helpful because infrastructure typically has a different and longer life cycle than each individual app. So if you've spent much time in the Kubernetes and cloud native community or using some of the projects, you also know that there are a ton of innovative projects exploring new areas of infrastructure and security. I'll only be able to cover the most common here, but you should definitely check out the KubeCon or Cloud Native Con talks. The videos are great. The Kates and CNCF blogs, the documentation, and other community resources to keep up on other topics. Even if you're just getting started with Kubernetes, it's important to keep certain things in mind so that future you is happy with the patterns the present you established today. If you're already running active old clusters, you might need to think about new topics or revisiting the old decisions that you might have made a shortcut on before. Let's talk about some of those decisions. So there's a lot out there, and we're only going to talk about some of the most common. So there's good infrastructure habits. First of all, we think it's super important to be ready to upgrade. You may have to do this on short notice, and you would have seen that in a few cases recently. So while the community is great at responding to vulnerabilities and issues, sometimes an upgrade is necessary if there's not a sufficient mitigation. Related to that, automate, automate, automate. You won't do upgrades if it's painful to do them. So using community tools that can help you minimize the pain of that is time well spent. You wouldn't want to have been stuck on an old version of Kubernetes that wasn't supported, or stuck trying to manually roll out fixes to, say, the runc exploit. The community response was great, but you did have to go and make sure that you redeployed a new version. The next one comes a little bit from the field too. So keep the abstractions tight. You don't want leaky abstractions. And really what this means is when you're setting up your infrastructure, it's really best if you can minimize interactions with other levels of the stack. So if your application doesn't need to know where it's running, that's the best case. Some folks that we see end up using host mounts. As an example, we went to one environment where the host name and some other host paths were mounted actually read-write by accident into every container. But just an example of the sorts of things that you should ideally not need to mount into your container, the sorts of things your app doesn't necessarily need to know. Those sorts of things can make it harder to make your app portable. It can make it harder to make changes like upgrades and other configuration changes. Now, in the infrastructure layer too, API access control is a topic that fits in here. So the Kubernetes API has what's called role-based access control, in contrast to the attribute-based access control that was introduced earlier. And it's a really powerful feature for keeping a lockdown on who can do what in the Kubernetes API. As we mentioned, the Kubernetes API is super powerful. It lets you deploy new workloads, set policies, configure how the cluster runs. So that API access control is super, super important. And what we often see is a lot of folks getting cluster admin, which is a sort of global administrator role, especially early on in a cluster's life cycle or in a Kubernetes adoption cycle. So it's really time well spent to think carefully about how you'll plan for user and group access. If you're using a cloud provider, there may be some integrations with identity and access management. And if you're using another sort of identity provider, it can be very useful to get your groups and other metadata set up now so that you don't have to come back and take down permissions later. That can be really important because the API access control determines what can run and also who can, for instance, exec into containers. So beyond infrastructure, let's talk about applications, what you can do to improve the security of your applications from a sort of workflow and general practices perspective. So many of those here may be familiar with the basic structure of a Kubernetes app specification, but first, let's zoom out and look what it tells us at a high level, and then zoom back in and look at some of the fields you might not have encountered before. So here's just a simplified app YAML. This is a deployment, and I've elided some of the fields just because they don't add much value here, and it's a small slide. We find it's really productive to focus on the deployment, the stateful set, or some equivalent resource versus the container or the pod, because this is the place that you have basically all the context you'll ever get. It's the resource that most people interact with, so that's what your developers and your ops people are going to be looking at, especially when compared with a single container, which is more of an owned resource than a top-level resource. There's a lot to do in each other area, but the deployment's a really great place to anchor your worldview. So let's start by reminding ourselves of all the data found in a single spec for a simple application. I've added some features that may not be necessary in every application, just as an example. This is ultimately a pretty standard Kubernetes deployment spec with some of the details collapsed. So right at the top, you see some operational metadata. So in our example, we've got some labels that say sort of what the application is, and then also some annotations that help us understand what's going on with it, maybe who owns it, which team, and then how to contact them in the case of an issue. The annotations add things sort of about the app, and we find a lot of people can productively use that to help other people understand what the application is. Next, you start seeing things about, say, what the application is. What code is going to run when we get this started. And the cool thing about images too is that while they have references that are pretty like this, they also have cryptographic digests. So you know exactly the contents of the application that will be, or the container that will start, the file system and the initial configuration. Next, we can see which sort of volumes it can access. So this can be storage or secrets and other types of things. And finally, how is it exposed? So outside of the cluster, how will people access it? In this case, we've got an HTTPS port open on a load balancer. So zooming in on the description of the containers, we see some more options describing what process will run when the container starts, whether there are any resource limits to prevent a runaway train from impacting neighboring deployments, additional storage options and privilege options about, say, which Linux capabilities will be included when the container starts, whether the file system will be writable or not, and then details of the environment and any sort of disk or secret access. And beyond that, more sophisticated applications might have network policies, more detailed storage, configuration maps, health check procedures. You can even have custom resources and other things that I may not have thought of. Now, that's a lot of information, and a fair bit of it might have previously been hidden inside of a VM image and some supervisor config file or in specs across a mix of other systems. With Kubernetes, on the other hand, all this content will usually be committed in Git in some way or some other version control system and kept in the same place as, or at least nearby, the application code. And critically, we can get to all of this context later once the application is running. So we know not only exactly what the image was, but maybe where it is, which team or business unit was running it. Any annotations and labels that operations or dev folks added to help explain the application, the privileges that it has, including access to the host, to the Kubernetes API, access to secrets, storage, things like that, networking configuration, including policies, exposure, and other networking configurations, and the behavior. And we can find all of this together, anchored around the Kubernetes deployment. Really, at SecRox, we think one of the unsung heroes of Kubernetes is the API service. It seems kind of obvious, the tool's got to have an API. So I think a lot of people sort of take it for granted. But the very idea of having standard APIs and standard concepts for access to all these things, secrets, storage, networking, service exposure, ingress, and more, is super powerful. And that power can really change the game for security. Now, if you're experienced with Kubernetes, you might have spotted some things in that YAML that look off to you. Great. It sounds like you have a good eye for style. As with writing or programming, it can be useful to have a style guide that says how your organization will use the basic tools, the primitives that you have available to you. There may be more than one good way to set things up, but if you've ever walked into a code base or a written document where each person or each author has embraced their own style, it can be really difficult to understand how things work or interact. There's real power in consistency. Along those lines, many of our customers have adopted basic labeling and annotation schemes. As I mentioned, the responsible team is a common annotation, and some customers require that it be set before things can be deployed. You might find other metadata relevant in your organization, maybe a chat room handle, a phone number, or a department name. So consistent metadata can really help, especially in the response phase, when you're trying to understand what's going on and you need to ask someone a question. Remember, people are still in the loop. In the application and workload realm, knowing your images is actually also very important. There are a variety of techniques you can apply here, and I'll only briefly cover them, but deciding on a minimal base image can be extremely powerful. If you start with a rather large image, we see sometimes images with 700 packages installed. It seems a bit too many. If you don't know what's installed, there's little hope for you to understand the security posture of all of those components. Beyond that, minimizing your images and making sure that you install only the packages that are needed, making sure that you sort of lay out the file system in a predictable way, and that you have sort of consistent practices and styles around how things start can be very helpful. Similarly, metadata applies here too. Image labels can be very powerful to help people understand what an artifact is, because they can pull that later from the registry and understand what the artifact is. Sort of on the workflow side of things, and the standard procedure side, if you're just starting out, establish secure practices now. You won't want to do it later. And if you're already running, maybe consider which sort of things you can begin opting into. Similarly, in the sort of design phase, it's really important to plan for replicas to be killed in the case of a compromise. So we find that security response is really aided when the security team can decide that this application is doing something that is not okay, and there are some applications that they have sort of pre-clearance to respond to in automated ways. This can really help contain issues because adversaries don't get to have a foothold before they don't get to maintain a foothold while they search around for their objectives and try to work through their life cycle. Now we talk about secure practices. So how should we enforce them? Well, there are a couple options, and they include using pod security policies or other built-in emission controllers, using custom emission controllers, and the other approaches including like reactive monitoring and for instance, what you might get in a security platform or in some open source tooling that would use the Kubernetes API. But remember the user experience and the people. You might decide to use a mix of these approaches. For instance, we've found that emission control, including pod security policies, is best limited to either larger risks that require a conversation before you'd be comfortable using them and wouldn't be used normally, like the -- privilege mode, for instance, or things that individual developers and operators can always fix, like using the latest tag. It's always possible to find a digest or find an alternative tag. On the emission control front, I'll just put a plug in. One of my colleagues wrote a Kubernetes blog entry. So if you go to the Kubernetes website and look at the blog, there's a great explanation of how you can build your own custom emission controllers. And there's great documentation out there for pod security policies as well. So on the user experience front, remember, there's nothing that will get a security control thrown out faster than causing an outage or preventing the response to one. So while it might be tempting to say block everything that has a specific component or violates a certain best practice, it's really important to think about what you really want to put on the line here. More ambiguous issues like image components or lower severity vulnerabilities can often be better handled by applying a risk management approach. Teams can understand what the Kubernetes deployment is, how it's exposed, what privilege it's running with, all the other data that you get from the great context that Kubernetes provides before making an informed risk management decision. So let's move to our last big question. And this one we'll spend a little more time on. What are some specific security controls I might consider? So regardless of where you are now, you're probably running Kubernetes somewhere. You've got some workloads maybe. What could you do to up your game? So there's a variety of configurations we'll discuss here. I'll first take the first three. So a read-only root file system. This is one that we think doesn't get enough attention. It's a single Boolean field that you can enable in your Kubernetes spec that causes the / file system to get mounted read-only. And this is really powerful because a lot of adversaries, when exploiting, say, command injection bugs, will assume that certain paths are writable, like /temp. So if you don't have /temp writable, they can't introduce new software into your container. And because many of these adversaries are automated, they basically will give up. We'll demonstrate a little bit of the power here using a struts exploit in the next slides. Another is Linux capabilities. So there's a default set of capabilities that most containers launch with, and some of them don't need them. So if your application knows that, or if you know that your application doesn't need some of them, or if you can find out using runtime monitoring, you can reduce the capability set. One of my colleagues and I spoke at the B-Sides San Francisco security conference. There's a video online about this recently, using runtime monitoring to understand which Linux capabilities you might be able to drop. And finally, network policies. They'll be included in this walkthrough. Network policies are a really powerful feature of Kubernetes that's been around for, I think, at least 18 months. We find that a lot of folks haven't picked them up because either they didn't start with network policies, so they haven't gotten in the habit, and now it's too big a problem to migrate, or because they just find them off the beaten track and haven't taken the time to learn them and really understand how they work. It can be complicated, so I again, back to empathy. I really understand this. I remember when I first learned. So let's talk about those three first and come back to the last. So in order to avoid tempting fate, I've run this demo in advance. And here's how we can stop a struts exploit using some of the controls that I just mentioned. So the setup here is I deployed a real container in a real Kubernetes cluster here. You can see sort of the log of it, creating a deployment and pods. That container had an exploit from 2017, one of the famous struts command injections. So we deployed a vulnerable container with a read-write root file system, no special lockdown. And then we run an exploit using a very, very long curl, an HTTP request with an injection, crafted injection, that will download a tarball from GitHub, from a crypto miner release website, untar it, and start running. And you can see that in the off-the-shelf vulnerable deployment, we can use the command injection vulnerability to run that through a shell. So Java is supposed to be running, that's what the app is, but now we also have a process running called minerd, which is a crypto miner. And going back to the B-sides talk I mentioned, it's possible to monitor your container and monitor file writes to understand whether you can mark certain paths read-write and go read-only for the overall path, for the overall file system. So as an example, we found that with this container, it does need to write to user local Tomcat upon startup, but it doesn't seem to write anywhere else, which makes it possible to write a read-only file system and declare user local Tomcat as a volume in the Docker file. There are, at least two ways that you can accomplish this. We typically like the declare a volume in the image because it can preserve existing content. But you can also mount an embedder in Kubernetes. It's a type of volume that exists on the host as sort of scratch space, but doesn't survive after the pod dies or is rescheduled. So after updating to declare a volume in that image, and upgrading the deployment to just use the new image with a volume, and changing the config to specify a read-only root file system, we do the same thing, set up a kubectl port forward, and then try to use the same crafted HTTP request. And when the exploit script attempts to download the miner.tgz to introduce new software into the container, it errors and says there was a read-only root file system, or the read-only file system here. I'm not allowed to modify this path, and it just dies. And you can see then when we exec to find the commands that are running, that it's just Java. The miner didn't get to unpack, and therefore didn't get to run either. So we can talk about Linux capabilities as well. So again, this is taken from the community talk we gave before, but looking at what capabilities are required or potentially required by the application. We can see that while we weren't using tar in our normal app, exploiting the command injection used tar, and it used certain capabilities. And if we know we don't need those for our application, we can remove them. So Linux sort of breaks up certain privileged actions into your capabilities, and you can say, even if, regardless of your user identity, you can drop the ability to, say, change ownership of files, which is the first capability shown there, or change file owners, or set IDs on files. And if we drop all security context, in the security context field, we can drop all capabilities because we don't need them. Now when we run the same script, even with a read-write file system, when tar tries to change ownership, it's not permitted to do so. And finally, network policies. So I mentioned that they can be a little bit difficult, and sometimes folks haven't enabled them. This is just an example of a visualization of these policies. We find that there's a lot of power there, but configuring firewalls is never easy. And while Kubernetes gives you sort of the right abstraction here, you get to specify which pods can talk to which pods on which ports, ingress and egress. It can be a little bit complicated to understand the full effective graph of what's possible. So just in this example, we see some active connections obtained through runtime monitoring. Those are the solid lines. And then there are some extra connections that are allowed using the dashed lines. And we find that most folks either don't have any network policies or have some overbroad ones. So it can be really key to sort of network segmentation to check out what network policies are. There's some community resources, including basically recipes for how you can deploy different policies, or there are products that can help you understand those as well. So we've covered read-only root file system, Linux capabilities, and network policies. Basically, preventing modifications to the container file system, preventing any command from executing certain privileged actions, and applying network segmentation. And together, those really do eliminate a fair number of the things that opportunistic adversaries will try to do. We found with some HoneyNet research that people are kind of lazy, and when they try to inject code, they'll often assume that /temp is available. They'll assume that dynamic libraries are available. So going back to the images even, if you use something like Alpine, which uses a different libc variant, you can just stymie these folks who aren't trying too hard. So let's move on to the other controls. So host mounts, like I mentioned before in the infrastructure section, the more you can avoid knowing anything about the host, the better. This also preserves some of your flexibility to move into serverless or nodeless platforms in the future, where you wouldn't have the same kind of host mounts. And sometimes that means application changes. Sometimes applications are built to understand something about where they're running. You need some unique identifier for the host or something like that. It's best if you can avoid that, and good to think about that early on as your application is moving to Kubernetes if it's not there already. Next, we can talk about service account auto mounting. So again, a callback from the infrastructure hardening section. API access control is really critical for users and groups, definitely. So you don't want to have too many users who are able to, say, modify production, but also applications can have access to the Kubernetes API. And if you don't need your application to speak to the Kubernetes API, you can disable auto mounts on the service account itself or in the pod spec. So for each pod, you can say, I don't actually need a service account. Please don't give me one. And that's found in the security context, if I recall correctly. Next, the environment. So this is kind of a container specific thing versus Kubernetes, but the environment is not a safe place to store things. Secret things at least. So if you end up using the environment for sensitive things, maybe connection strings or API tokens, please don't. Kubernetes has great secret support, and you can mount things in as files, which makes it a bit harder for others to observe them. It's important to remember too that there are new, while containers can help you do security better, there are also new infrastructure components. So things like the kubelet API server, and in some configurations, those can leak things like the environment variables, which means that you'd be better off not putting secret things in those. And finally, one that maybe doesn't come up in security circles as much, resource requirements. But maybe it should, because availability is part of the CIA or AIC triad, the confidentiality, integrity, availability triad. Now, if someone can exploit an issue in your application and cause sort of a rolling outage in your application, that's not good. And Kubernetes does have the ability to specify both requests, which you should use. All of our customers at scale basically require resource requests at least. But limits are also very powerful. For CPUs, you can specify that this application should not take more than a certain amount of CPU, and that CPU will then be niced down, so it will never exceed that limit if needed. For memory, it's a little bit more blunt force. If you exceed your memory limit, you'll just get your container or the process killed. So we tend to see those set to rather high levels that are maybe a large portion of the node's available memory, so that a true runaway train will get stopped, but normal application operations won't be impacted. So those are some of the main configurations that we think people can adopt. We think especially read-only root file system is something that many apps can do. It's a relatively easy configuration change. might be able to head back to, or if you may recall, at least the earlier slide where we added certain configurations. It's just a single Boolean inside the security context. It's rather easy to opt into. And then in most cases, you can either deploy a volume or an empty dir to handle it, to handle any writable file system needs. And of course, if you mounted a persistent disk or other persistent storage, it's not affected by the read-only root file system. Now, with all these configurations, Kubernetes gives you advantages because you can test them, like I mentioned. So they get the best ones of these are committed as configurations in your deployment YAML or in other places, and you can test them on your laptop, test them in dev, in QA before you roll them out to production. So we think people can really confidently explore these. For instance, when we were getting to a read-only root file system in our application, we would just push it to CI, and if CI passed, we're good to go. Of course, we do the manual QA testing as well, but we can move forward with pretty good assurance. It's important to note also, for instance, some of these, like network policies, that you do have to have some infrastructure pieces in place before you can use them. For instance, you may need to opt in to a network driver that supports network policies. And depending on your cloud provider or the way that you manage your host, you may need to take some action there. So at this point, we've covered the main topics here. If there are questions that you have, I believe they're being moderated in Zoom. If you think of one later, feel free to email me. I'm just C, the letter C, at stackrocks.com or at Connor Gilbert on Twitter. And then there's also a place for more resources on the web. So stackrocks.com/CNCF.
Awesome. Thanks, Connor, for the great presentation. So like Connor said, we have some time for questions now. If you have any, please drop them in the Q&A box at the bottom of your screen, and we'll get to as many as we have time for with the next 15 minutes. So our first question here, can you talk a little bit about how RBAC differs from admission controllers from a Kubernetes security perspective?
Sure. So I think of them really as two kind of separate but related topics. So your RBAC will help you prevent unauthorized folks from modifying Kubernetes resources or control how people can access the resources that are already deployed. Admission control, we typically, there are some built-in admission controllers that help establish certain things, like namespaces have to be created. You can enforce certain security policies with admission control as well, but those tend to be about the application because they're in the request path for when resources are getting created. There are some interactions, for instance, users and groups or service accounts can be linked to pod security policies, but for the most part, I think of them as separate.
Great, thank you. So another one, what is the best place to hold the network policies YAML? So this attendee is asking, they may not use network policies for the dev environment, but only for staging and production.
Okay, that's an interesting question. So I think I would actually recommend trying your network policies basically as many places as you can. And perhaps in dev, you might add another network policy, because in general, network policies, once you've selected a pod, now traffic is restricted. So you can add another policy that allows different access. So you might, in fact, better be able to have the same policies apply everywhere and add a little bit more in dev, for instance, if you need access to debug ports or something. Now, as to where to actually store them, we found different practices in different places. I tend to prefer keeping the network policies basically right next to the deployments that they control. So often it's very productive to have ingress rules for which service, who can be its clients. And that lends itself to being stored right next to the deployment YAML, the stateful set, that sort of app spec. That can be a great place to put them. Other people like to manage them centrally, although that can have some more issues just around keeping everything in sync. And then just sort of nuts and bolts. It can be nice to keep them in separate files to avoid merge conflicts. Just if you have like a central policy, a big list, and people are adding different policies at different times, it could be nicer to have sort of groups of policies in different files.
Great. How do you check that Kubernetes itself has been set up correctly? Like dashboard, metadata exposed. Can you talk a little bit about that?
Sure, absolutely. So those are some important security controls. The dashboard, if you don't need it, it's best to just turn it off. Certain cloud providers will default that way. Certain cloud providers and other systems will default to deploying a dashboard. And also the metadata server, for those who don't know, is a cloud provider service that can be sometimes accessed from your applications if, for instance, your application has a server-side request forgery issue. We saw this with Shopify bug bounty, and I always like to give credit to them for publishing this bug bounty so everyone could learn about it. So how do you verify that the cluster is set up correctly? It's going to be some mix of looking at resources like network policies and other configurations that sort of exist in the Kubernetes API. And then another great place to start is with like the CIS Kubernetes benchmark. So the Center for Net Security publishes certain guidance about, say, important controls that are set on the API server. How you actually assess that will differ based on how you're running Kubernetes. So if you're running in a managed service like Google Kubernetes Engine, you'll use the cloud provider APIs to understand key features that are turned on or off. While if you're operating your own cluster, you might have a config file that lists more of these, or you could just look at the master and look at the command line arguments to API server. So the mechanics will differ just based on how you've deployed.
All right, we have a lot more questions coming in now. What is the best way to identify the Linux capabilities required by a container?
Good question. It's a bit of an interesting. So we did a bit of a talk on this using runtime monitoring to help generate more secure configs at B-Sides. I think we can try to maybe get the link onto that landing page. I'm signing some people up for more work, so maybe wait a little while and you'll see it. Or search on YouTube for B-Sides San Francisco 2019. So the technique we used there was instrumenting the kernel's capable function, which is used to check whether capabilities are present. That's one way. Another is to just sort of know what your application is doing and guess and check. It's a little unsatisfying as an answer. But if, for instance, you know, there are certain ones that are more obvious. So if you know that you're not sending raw packets, you can drop capnet raw just sort of out of the box. If you know you don't do file operations, you can drop a few of those file-related capabilities. So that is kind of an open area. But certainly like net raw is a good one to drop, in my opinion.
All right, so going back to what you were talking about with namespaces, should we limit the resources on the namespaces? What's your advice there?
Okay, that's a good question. So I actually should have mentioned more about namespaces. They're a really natural security boundary, so it's a very effective control to organize your things into namespaces. When we come to some place and see that everything is in default, it makes us a little sad because it's hard to understand what the application is, and we empathize with the folks who are going to have to respond and understand which of the 50 services here belong to which sort of team. So using namespaces as a first go is important. Now for resource quotas, at the namespace level, we tend not to see as much value there, at least from a security perspective. That seems more like a budgeting and sort of resource planning issue at the namespace level. The place where I think it's most important from a security and availability standpoint is more about individual deployments and not being able to be runaway trains that sort of cascade through the cluster. So especially memory limits, that's on each workload. I think those are strictly more important than namespace quotas.
All right, let me see here. So for creating a unique application user in the container and using it to run the app and accessing the volume mount, is that a good practice?
That is a good practice. So it's best not to run as root in the container because most don't remap user namespaces between the containers, the container engine and the host. So it can be really productive to use a non-root user. If you're going to use persistent storage, it is really important to have a UID or a GID set up in advance so that you can make sure that the storage has access to that. That is a good practice. And you configure that in the security context. There's sort of supplemental groups, I believe. You're testing my API knowledge off the top of my head.
All right, so I'm not sure what your familiarity is here, but talking about CNI, are there any security policies there that can be configured?
So I'm less familiar with the specifics of the CNI providers. This is the container network interface, but network policies are the primary way that we interact with network interface with the networking plugins. So the network policies I mentioned, for the CNI providers that know about network policies, they'll read the network policies from the API and enforce them. So you'd be configuring them via network policy YAMLs. And if you're deciding sort of your infrastructure stack, it's important to have a provider that supports network policies. Most of the main ones do, but you may have to opt in your provider or management tool.
All right. How can we switch to root user if the container is configured to run as a non-root user?
I didn't mean to imply that you could. It's best practice to run as a non-root user, and then you would stay non-root. The issue that I was, I'm not sure if it's a response to an earlier answer, but the issue I was pointing to was if you do run as root by default, which is the default, then you're in, you could be in trouble. But it's not really, as far as I know, risk from sort of elevating back out. That's not what we commonly see.
All right. Is there a recommended maximum size of Docker image with code base to host in Kubernetes?
Okay, yeah, I don't have a number for you, but the size of the Docker image certainly does sort of point to things that would be problematic. So if you have a really, really large image, chances are you've got lots of components, and lots of components means lots of stuff for adversaries to take advantage of, but also potential for vulnerabilities. So, I mean, a rule of thumb, if you're in the tens of megabytes range, you're probably pretty good. If you're in hundreds, you may be fine, but there's probably room for improvement. If you're above a gigabyte or so, that's when I would start to be really wondering what's going on in this image. Usually, that would point to something. Maybe storing too much data in the volume or too many components. So and also could impair your availability if things are going to reschedule pods. You don't want to have to wait for a gigabyte to download every time.
And then is there a number of general security profiles you would recommend for containers in a typical application?
So I think one of the cool things about containers and about microservice design patterns is that you can tailor your policies pretty well. A lot of applications, depending on sort of what you're doing in the container, a lot of the applications that you're running, it's likely that you don't need much in the way of host access or even persistent storage sometimes. If you're running API servers or caches or that sort of thing, it's likely you don't need much elevated access at all. So read-only rootfs is typically something that most apps can do, or at least opt in with a volume to a read-write on a specific path. I think network policies are pretty generally applicable. You just have to get the workflow right to make sure that you're testing them and not causing outages. If you're talking specifically about like seccomp secure computing profiles, I don't have one offhand, but the runtime defaults tend to be at least they tend to at least cut off the worst possible bad things.
All right, let's try and get a couple more here. Is there any embedded security in container/pod other than the app software setting?
Is there any embedded security? I think I'll take the question as asking, like, does a container help you contain things, maybe? And the answer is yes. There are certain, it does help to run things in a container. Containers aren't solely for containing. You can think of the visual metaphor as a shipping container maybe is more productive than a locked box. but just the fact that the container mounts a specific file system, and the fact that you can configure a lot of the controls, like the read-only rootfs, the dropped capabilities, the different user identity, that can be beneficial just to keep apps from having to know about each other, or designing in a way that they're independent.
Great. I'm going to close this out with one more question here. What are the advantages to having enforcement via Kubernetes versus in a separate control layer?
That's a great question. So, and it speaks a lot to the way that we've designed our product, which is to use the Kubernetes features that we can as much as possible. The benefit of that is that you've got portable, robust, and usually scalable controls. So, for instance, if you work on getting a network policy set up, it'll apply basically anytime anywhere that you have a CNI provider that knows about policies. If you set read-only rootfs, it's going to be there always. If you work on the sort of native controls, you're setting yourself up to operate wherever Kubernetes operates. Whether you switch cloud providers or you go in-house, you're sort of future-proofing your security.
Great. Thank you so much, Connor, for going through all those questions quickly so we could get to all of them. So that's all the time we have today. Thank you, everybody who has joined us, and for all of those great questions that were asked. The webinar recording and slides will be online within 24 hours. And we look forward to seeing you all at a future CNCF webinar.